Today maybe it's a little bit long, and we have two more lecture we will discuss regarding this chapter 4 because it's one of the important chapters that we have in our book. Anyway, let us first start about what is combinational logic and what we have. In the digital world or logic circuits, we have two type of system. One could be combinational and another one should be the sequential. Should be the sequential. Conventional circuit uh, consists of output which is variable, uh, logic gates, and also output variable. As also you will see the box here or block diagram that I show here, we have some input which it should be n number of input, and on the other side we have m number of output. Then we have one box between. Something will enter, something will be out. Then between them, this is our work, our combinational circuit. Uh, but to know these, we have some concept that why we should use them. In the combinational circuit, we have some types of box. Means that inside of that box, we have some variety of the machine or system. One of them should be multiplexer, which is work as the selector for routing the data, the processor, memory, inputs and output. Or this multiplexer, maybe it will route the data to the correct bus or port. We have something in that box that we call a decoder, which are using selecting the things like the bank of memory and then the address with the bank. And this is also the function which is needed to decode the instruction and determine the operation to perform. Maybe inside of our box we have one another tools which we call it encoder, which are used in various components such as keyboard. How we should analyze this procedure means that to obtain the output Boolean function from a logic diagram. This process we will follow. First means that we should label all gates output that are a function of output variables with uh, our arbitrary symbols and determine the Boolean function for each gate output. In the second step, we can label the gates that are function of input variable and previously labeled gates with other arbitrary symbols and find the Boolean function for these gates. In the third step, we should repeat the process outlined in step 2 until the output of the circuits are obtained. And step 4, by repeated the substitution of previously defined the function, output the output of Boolean function in terms of input variable. If you don't understand them proper, don't worry. We will talk more about this process. But this is the whole process that we need to design with the combinational circuit. Uh, with the combinational circuit. Okay. As I tell you, the process to design with these circuits, they have five steps. One is that which we call it specification. One is that formulation, then optimization, technology mapping, and verification. Then in any design, even you have the same process. If you want to check your design, or if you want to do your design job, you should pass uh, the same process for your work. Let us see one example. Suppose I have the same mapping design or same mapping gate uh, for my system. As you will see here, I have some inputs and some function, as you see, F1, F2, and so on, which all of them are shown to this shape. First, if they give me this gate, my first job is that I should check the output from each part. Okay? I mean that if I want to uh, if I want to see the logic which is design this shape or this map, each part I should calculate. First, if I start from the output of T2, I will see that this is the AND gate between three inputs of A, B, and C. Then for T1, I will do for A plus B plus C, as you will see the gate. Then here I have some output that I can calculate it here, which is equal to AB, because I have or and of AC and of BC. All of them should be or, that it's equal to F2. Then if I take the NOT from this F2 and then we'll AND it with T1, it's become T3, as I written here, F2 NOT and T1. Okay, what are these? All these points that I said are how we should pass the first step. Then uh, very simple. First step is that I should find the output from the gates or map that they will give me from each point. Okay. And then suppose if I want to calculate real F1, F1 is T3 plus T2, which T3 itself is F bar 2 uh, into T1, and it's equal to A naught B C naught plus A naught B naught C plus A B naught C naught plus A B C. Okay, now I found what is my F1 and what is my F2. Let's go ahead. How many inputs I have? If I check the number of the inputs and the output that I have, simply we can understand that we have three number of inputs. Then the arrangement for three number of inputs is equal to 00 up to 7. Okay, then I can put 00, 001, 010, 011, 100, 101, 110. Then by the formula that I have, simply I can calculate F2, simply I can calculate F1, simply I can calculate F bar 2, suppose this is F bar 2, and T1, T2, T3, and F1. Okay, how I calculate this truth table? I calculate it based on the uh, relation which I extracted from these circuits. Okay, then as I will see here uh, in these the relation between these. Okay, what should be the next? Next should be very simple. What is that? I can put these inside of my Carnot map, and then from my K map, I can simplify the equation, and then maybe I can have the better design, or maybe the better gate design for my question that I have. Let us see one more. Means that suppose I have another example. I have some input BCD and some put some output exit 3 number, as we know. And we have the table which is going to convert the BCD and exit 3 codes. If you remember, when we uh, speak regarding the codes and coding, I tell you that again we will return back to this coding part. This is the exact one. What was exit 3? Exit 3 was whatever inputs that I have, I will add it with 3. Means that instead of start with number 0, it will start from number 3. Number 1 is number 4. Number 2 is number 5. Something like that. Then, if you will see in this table that I have, inputs is the PCD inputs, which have 4 digits or 4 inputs, A, B, and C. And A is the most significant, means that it has the mm, valuable, most value. And D is the least significant, means the D is at the end. The output that you will see is exit 3, which has the W, X, Y, and Z. It means that this value is A, if I can write it, okay, and this one is D, this one. And here, this value is W, and last one is Z, like this. And then we are searching for some internal operation, or exactly now we are searching for that box. You remember when I said the combination or secret? We have one box, which inside the box there is the logic that we have, and outside is the input and output. Now we are searching for inside of that box. If I want to do the formulation for this exit 3, BCD to exit 3, the exit 3 codes is easily formed by adding the binary 3 to the binary or BCD for the digits, and they are impossible inputs for both BCD and exit 3. It can be assumed that only valid BCD inputs will appear, so the 6 combination not used and cannot be can be treated as they don't care. Why? Because in the BCD number we have just number 0 till 9. Then the number more than 9 means that more than these 9, maybe we can put as they don't care in our K map. Let us see. Simply I have done for each variable here, I mean W, X, Y, and Z. Any of them separately can have the K map 4 and 4, and that case are uh, don't care case, which are more than 9, and you will see that the mapping should be like this. Then the next step for me is to simplify them. The simplification is very simple. I should find the loop to make them simple for any of them. Let us see. Suppose for the first one, simply I can do something like that. This don't care, I can take 1, and then these I can take 0, and these I can take 1. Then if I take that, my output should be D naught. And same way, if I'm searching for the parameter Y or output Y, then again I can take this 1, and this again I can take 1, then it can be CD plus C bar D bar. In the same way, if I'm searching for the X, I can have the loops, and the output should be B bar C plus B bar D plus B C bar D bar. And then we can have the W as the output, and we call it A plus BC plus BD. And as I was searching for the 4 output with the help of Kmap, now I simplified that, and then I can write the relation between them in this form, means that this is the midterm part and don't care part as I had in the formulation, and then do the uh, minimization and draw the logic. Let us see one more thing. This is also the same. That suppose they give me that W is equal to mean term of 5, 6, 7, 8, 9, and we have some don't care condition. We are going to put them inside the K map, and after that we do the simplification for any of them. Very simple, and this is the output that we are searching for. That this is, I say that Z is equal to D bar as we saw the K map. Z is equal to D bar. This is my Z here. And Y is equal to C plus C bar D bar here. X is equal to B bar C plus B bar D plus BC bar D bar that we can see here. And W is equal to A plus BC plus BD, which is shown here. Now, what we design the logic diagram for BCD to exist code converter. What we learned from this example was that we start from two ways. One is that first I showed you the some output, and based on the logic output, we design the circuit. And on the other part, what we have done, we had the relationship between the input and output, and based on that, we put it into the K-map or Karnaugh map, then do the simplification for that, and then we draw the simplified form of the K-map. Okay. Now, that was the whole process. When we are working with combinational circuits, we will follow more examples. But now we should learn some famous tools or some famous bugs inside of the uh, parts that we have. Means that now we have some famous machine or some famous tools that most in some design or most of the design we will use them. Now we are going to review them. But before I start the second part for today lecture, please tell what I tell you. I give you one simple example about the combinational circuits. Now we go inside the box to review what we have inside of the box. Um, Inside the box can be some adder or some subtractor. We are going to see what is half adder, what is full adder, what is half subtractor. Okay, as I said that we have something inside the box that we call it adder or subtractor, and for the adder we have two parts of half and full, and for the subtractor we have the half subtractor. Let us see what are these. See, here I saw the relation between 2-bit half adder. As you remember, or maybe these are some definition that some parts are fixed and some parts we should see the design. Okay, then be careful, please. Half adder is the combinational circuits that perform the addition of 2 bits. And these circuits needs 2 binary inputs and 2 binary output. If you see the truth table that I show here, I have X and Y as my inputs, and output should be 2. You remember that when we do the add for 2 bits, we had two parts. One was carry and one was sum. Okay. We show the carry as C and we show the sum as S. Okay. Now let us see. I know the carry for 0 and 0 is 0. Carry for 0 and 1 is 0. 1 and 0 is 1. 0. And just in the case of 1 and 1, I had carry. On the other way, uh, I had S that we call it sum, and we remember that 0 and 0 was the summation was 0 and 1 and 1 was 0. Rest of the case, this is 1. Okay. Now, if I want to write the relation for C, means that in the case, I should write the case which C is 1. C is 1 just in the case that X, I have X and Y, as I show here. Okay. And what is my S? S is just, I should write the case, which is S is 1, and it's equal to X bar Y plus X Y bar, okay, as the S. Then simply I know that this is XOR, and next one for the C, this is AND. Then I can show the design. If you see here, I can show it as here, as S is XOR of X and Y, and C is AND, or I can show this equation, means that X bar Y plus X Y bar, and C is equal to X Y. This is the design that we can show for half adder. Half adder, why we call it half adder? Because it can do just with 2 bits. Okay, let us go ahead. You remember that we had, suppose in the binary addition by hand, what we will do? You can add two binary numbers on column at time starting from the right, and just like you add two decimal number, we will do the same. Just the difference is that 1 plus 1, instead of 1, it's become 1 0, means that it will go one more digits ahead. We practice this. Okay, we can do, suppose if I start from here, 1 and 0 addition is 1, 1 and 1 is 0, and 1 1 will go for the next. Okay, this is the carry that I have. And then 0 and 1 is 0, but because I have 1, it's become 1 0. Then again 1 1 will go there. 1 and 1, it's become 1 and 1, and at the end I have 1 1. This is what we will do with hand. Now, same job we will do with the um, half adder, and we will see here, previous time we'll see. The output is exactly what I have done with the hand, and design is whatever I have done for you with it. Then this is inside of the box that at the initial stage of today lecture I tell you, or sometimes people will use it like this. These are the inputs X and Y, and these are the output as the carry and summation. Okay, again, we will see the same concept, means that these slides are not new. This is exactly repeated things that we have. Just I want to show you that we have X and Y as input, and C and S as the output, and relation is shape. But uh, we can uh, do the one job. One is that I can simply write the equation between them, or I can analyze that the relation between X and Y is XOR, and for the S, it's exactly the AND gate between the my inputs. Okay, now let us see our box, something like full adder. What is full adder here? If I had the full adder, then I can have the combination of two half adder, which is going to become my full adder. As you see in our hand example, what we have done, we are carrying the carry, or we have the carry from the last step. Okay, It means that I have one half adder which will act for first bit, then the output of this half adder will go for the next half adder, and like this again, next half adder, next half adder, next half adder. All this we can call it full adder. Okay. Then that is why in my full adder I have one C in, which is carry in. Okay. And I have one S, which is output, and C out. Okay. Let us see what we have in full adder. Means that one of the perform the addition of these 3 bits we show here. It can be the exactly half adder. First, we will do the summation between first 2 bits, and the output will go for the next one. We will calculate the carry and sum again 2 bits, and then result of 2 bits to the next bit. Like that, I can have this table. It's not difficult. You have done it with the hand. And we will see the combinational circuits that add 3 inputs bit to generate the sum and carry bits. If again I want to have the circuits or logic gates between these, simply I can see just the output number C and just note down the case number 1 inside of my uh, Carnot map. As you see here, I show the K map here, and because we cannot make the simplified for uh, the output, we can see that S is equal to X bar Y bar Z plus X bar Y Z bar plus X Y bar Z bar plus X Y Z. And on the same way, for the C, I can see that if I note on the just one there, I can little bit do the simplification for that, and my output is X bar plus XZ plus YZ. Then very simple, I can just draw the gates for this S and C and show it like this. Then you will see that it's not difficult. What we learn is that the full adder is combination of 2 half adder, and the output of first half adder will go for the next half adder, and finally we will have the S and C for that. Okay, then it can be the formula for the full adder, and which we already have it. Also, we can have some another implementation, which with the full adder we can also implement with uh, 2 half adder and one OR gates, as you will see the formula here. These are not much more difficult. This is exactly based on the true table that we have done to make yourself confused. It's exactly based on the true table, and it's not even uh, now difficult in this stage for you, and we will design. Then we learn we have full adder, which is combination of 2 half adder. We learn half adder, and then after that full adder. Now we should go for the next things, which we call it subtractor. You know that it's also the same. Subtractor is the one which used to subtract 2 binary numbers, and it can provide the difference and borrower as the output. Means in the adder we had summation and carry, but in the subtractor we have difference and borrower as the output. And basically we have 2 type of the subtractor. One is that half subtractor, another one is full subtractor. As you remember, when we review the addition and subtracting, we had the rule. The rule was this: 0 minus 0 is 0, 0 minus 1 is 1, 1 minus 0 is 1, and 1 minus 1 is 0. With one borrow, okay? We had the rule that we have. Same again we can have for the half subtractor between the 2 inputs of A and B, and we can have 2 output of difference and borrow. With the difference again, we will see that 0 minus 0 is 0, 0 minus 1 is 1, 1 minus 0 is 1, and 1 minus 1 is 0. And same for the borrow, which we will have one borrow here. Okay. If I want to note down the formula for the difference, I can see that simply it's XOR for A and B. And for the borrow, as the case of one that I will note down the formula for that, it's exactly A naught B. Okay. Then we learn subtractor is nothing by these, as you will see, one XOR between A and B, and one borrow with the A here. Even somehow we can make it little bit simplify with the help of K-map. So the secret diagram using the K-map is showing here, and while the logic diagram of half subtractor is uh, something that I show. Then for the full subtractor, we have the same policy or same path that we have for the half adder. What we will do, first we will calculate between 2 bits and then for the next bit. Okay. Same thing we can do for the 3 bits as the full subtractor, and which is the logic circuit which is used the subtracting of 3 single bits of binary. um, the truth table of that I show here, you can just um, compare and see for 1 minute, 2 minutes. Please just watch it. Then we will see the full subtractor circuits. It's also implemented with the help of two half subtractor and one OR gate. Okay, just see this table for 1 minute. Okay, now maybe you will understand that it's exactly nothing by subtracting the 2 bits, and then next bit will come. If we have 4 digits, say 1 and 2 with third, and then result of third with the fourth. But what is different? Different is that we should have we should have the borrow parameters and difference parameter uh, at the end. Okay. Then with that, we can understand that suppose if I had for the first one 0, 0, 1, I will do 0 minus 0 minus 1, it's become minus 1. 0 minus 1, 0, it's become minus 1, and then same things. But difference between 0 and 0 is 0. 1 and 0 is positive 1. 1 and 1 is negative 1. And 0, 1 is again negative 2. The only time you can set the 0 for difference and 1 for borrow is when your answer is minus 2. Okay, this is something that we should note down and have this rule. Same policy, we will put it, we will extract the formula of the difference and then put it in the K-map and then make the simplification for that, and we will see that if we calculate with the Boolean algebra or with the help of the K-map, same result we have, and we can have this circuit as the full subtractor. Um, these parts need you to again you follow my PPT and also solve it. Even you can read the book. In the book also, it has the same process which you can follow and do it very fast. Anyway, what we learned just right now till now is that we have the two parts. One is that full adder, one is that full subtractor. Now, if I want to have the ripple carry adder, or what I should do, I should have the machine which insert the carry and take the summation from each part and again pass the carry to the next stage, something like that. Okay. This is the 4-bit suppose bit adder. 4-bit adder. With 4-bit adder, I need four half adder or half full adder inside, and then I can do the adding job between them. What will be the case is that the carry propagation, which it will use the unstable factor for carry bits and procedure longest propagation delay for us. And the signal CI to the output for us, the signal CI to the output will become CI plus 1. This, what we have between these gates, as you will see here, to pass over the carry, we call it propagation time, which it has some key factor in later that we will see. Then, because this propagation delay, which will affect the output signal on difference time, so signal are given enough time to get the precise and stable output. This is something that we need for the later design that we will see. What I try to tell you is that maybe you will see that the system is very fast and carry will not pass over to the next part. Then they put some propagation delay or some stops that when this carry hand over to the next block, it will work and then do the summation for the next part. Okay. Then if I'm going to have the 4 bits of adder, we can have some design like this, which we call it Cali lock ahead generator, and then we can have this design. Don't afraid, it's not much more difficult. It's exactly some figure that we have, and we will learn soon how to design all of them very fast. Then the real 4 other bits can be something like this. By the relation that we have, we can have the carry lock ahead generator and then extract the S3, S2, S1, and S0 and C4 for my design. Okay. And the machine for the binary subtractor is something like that, which we can have the 2 job for that. I will discuss this machine later more for you, but just have this idea. When I can have some control like M here, when I put the M with this machine 1, then it will act as the subtractor. And if I put the M as 0, it can act as adder. These circuits maybe you should memorize. This is something that you should memorize it and know the structure. Even we have some example that you should test this with the truth table, then you will learn it better. Okay, have it in your mind. We will talk more about that. But one more thing that we have, it's overflow, as you remember when you will do the adding or subtracting work. That was overflow for the sign numbers, which also we should see. And we know it as the problem in digital computers because the number of bits that hold the number is finite, and the result that contains the n plus 1 bit cannot be accommodated like that. Overflow unsigned and unsigned number is exactly what we talked before. It's when 2 unsigned number are added and overflow is detected from and carry out of MSP position. And when 2 signed number are added, the sign bit is treated as the part of the number and end carry does not indicate an overflow. An overflow cannot occur after an addition if one number is positive and other is negative. And overflow may occur if the 2 numbers added are both positive or both are negative. What I show here, again, one BCD adder which cannot exit number 9 on each, and we know the key as the carry parameter here. I show in this table, but just see that I'm going to continue about this concept later. Okay, now, till now, uh, is there any question? Let me make your. What I wanted you to learn is that I wanted that all of you knowing two concepts. One is that full adder, one is that half adder, subtractor, full subtractor, and half subtractor, and 4-bit adder. Did you learn this or no? Any question till now? Okay, okay, no problem. Uh, then let us do one more attendance. Then I have just talked for 10 minutes and then we can leave the lecture. Turn on your webcam once more that we can do the second attendance for a school. And then uh, I just should talk for 10 minutes about some ICs and then we can leave for today. Turn on. Amir, I cannot hear your voice. Can you hear it proper or no? I cannot hear.
Yes, sir, I can
Okay,
hear you well.
okay, okay. Is there any question?
No, sir.
Okay, first page. Okay, now you can turn off, please. Monshi also, Raunak, Nafis, Buggy, Morshed, turn off, please. Okay, now let me see Victor, Satam, Napoleon, Eileen, and Shamim. Is there any question? Victor, Napoleon, Satam, Gilin, Shamim, any question?
No, sir.
No, sir.
Okay, good. Just I should talk for more 10 minutes because it's a little bit important for you when you are working with the uh, Proteus. Please turn off your camera, Victor, Saddam, and Shamim. Yes. Poppy, you come late, but no problem. Your pictures come late, but I will put it, no problem. Okay. Now, uh, what we should know that, you know, till now we understand that we have some gate, but I want to give you some extra, little bit extra information regarding the ICs and what is inside of these ICs. This part is little bit um, um, maybe whenever we have the lab or experiments, it will help us. But now I think that because you should do your assignment with the help of Pro Tools, okay, and you should have some idea about AND gate, NAND gate, and numbers. I think these some slides will help you more to do it. Okay, let us see. Just first, I should confirm that you have the screen or not, and then we will continue. Okay. Okay. Should turn this just sound. I should turn off. Anyway, um, just have this information. Maybe it's more, as I say, but it will help you later to design with the help of the Proteus, and then you can understand better. Okay. Um, we have some concept in the digital real design. Means that when we want to buy the IC and implement, suppose this full adder that today we learned, we have two concepts. One is they call it TTL, and another one they call it CMOS. Generally, this TTL family will start with the number of 74. Okay, suppose 74007404, it's hex inverter. And then there is some technology beside that that just right now I don't want you to know. But just remember that suppose if they call it 74S04, it's the Schottky TTL or low power one that they have the L. Advanced Schottky TTL is A, and advanced low power that this is AL. Okay. First things that I want you to learn is that TTL will be start with 74. This is the first. On the other way, we have another technology that we call it CMOS. CMOS ICs will start with 40. Okay. And for suppose one AND gate, we have CMOS and TTL technology at the same time. Which one is faster? CMOS is faster, and the consumption power for the CMOS also is less. Generally, these CMOS are working with 0 and 5 volts, and uh, TTL1 will work with a range of -50 to +50, or sometimes maybe more. But the regular one is like that, and maybe some of them also will work with 0 and 5. Okay. Why we have two type of technology? Because TTL1 is little bit old technology, and CMOS is the new technology for that. Uh, as you will see here, TTL is device. Normally we will use 5 volts, and for CMOS we will use 3 to 18 volts. TTL logic means that 0 and 8 volt is that, and CMOS is 1 to 5 volts as the input. Here I give you one data sheet for 7400, which is the NAND gate. And this number, from next time when you start to work with the Pro Tools, you can understanding better. Means that with the help of the data sheet, you will understand the specification for each IC. It could be TTL or it could be CMOS, no different. And you will see these data. These data, it's something which help you when you are designing the real system. Suppose how much current you need, how much voltage you need, what is the maximum current that you can have, what is the minimum one, and so on. This number, next time when you implement your design with Pro Tools, you will see exactly, suppose for NAND gate, you will see that it's the 7400, or maybe CMOS. Let us see it from much more near, that what is the difference between suppose 74 and 74S, or LS and AS and ALS and F. Okay. You will see, suppose the propagation delay that just right now I talked with you. With the 74 is 9 nanosecond and S is 3. Okay. Suppose C, F is again 3 nanosecond. Then you will understand that if you use the 7 for F for your circuit is much more faster. Or let me compare in another parameter, something like the clock rate or timing frequency. You will see that this is 100 megahertz, means that it's much more faster than 7. Like these are the um, data that you can get from your datasheet, and even see here in the CMOS of 700 400 and 740 TTL, you will see that the difference between the voltage inputs in the high is minimum is suppose 3.5, and here this is 2. Means that whenever you will design, maybe you can extract more voltage or inject more voltage for your circuit. Generally, what we have for our circuits, this is the real shape or physical shapes, and these are what we have inside of our ICs. Suppose the IC's number 7404, it has the 6 number of NOT gate inside. Okay. Then simply you can, whenever you need the NOT gate, you can have one of these and have the 6 number of these gates and do the wiring. Or suppose uh, some OR gates like 7408 or 7432, like that, you will see that we have 4 number of OR gates or AND gates for 7408 inside of our chip. This is something that we have working with that, and whatever we will design, we are working with these schematics mode, and this is the physical one when we have it in our lab. Okay, one example, suppose if they tell us that do this example, uh, we all want to show the f with x2 bar x3 plus x1 x2, we will see that simply first I should add the VCC, means that voltage and ground for my IC. As you will see here, these 2 pins are voltage and ground. And then I will implement my logic very simply with the help of one NOT gate and one OR gate and one AND gate, okay? Which finally I can have my F here as the output. Means that this is exactly what we will do in real world. What we have done on paper, it can be implemented with the help of these ICs and these integrated circuits. What I wanted to tell you that whatever we will design from this lecture, you can do it really in the real world. It's not something that just it's simulation or uh, it's something like just theoretical, but it's exactly practical point. Please do your task from this time with the help of Proteus and try to have some idea about the inside of your ICs. Okay, it's okay for today, I think, and we can stop now. But if you have any question,